All right, here we go. Maybe, after I get the video going. Y'all are slow.
I'm not complaining.
I am, because y'all are slow.
Well,
Cool. All right, we're going to buzz through this really quickly. Do not stress about this. I just want to talk about it so that you are more complete. Polyprotic acids, acids that can furnish more than one proton, they dissociate one proton at a time. So if I've got something like sulfuric acid or phosphoric acid, it's not that all of those dump out all at once. Okay? So the conjugate base of the first dissociation equilibrium becomes the acid in the second step. So the first one comes off, second one, third one. As you might expect, for a typical weak polyprotic acid, the Ka of the first hydrogen ion is much greater than the second, which is much greater than the third. This should make sense because, for instance, like phosphoric acid, the phosphate has a charge of -3. So that's going to hold on to those three. When the first one comes off, it's going to hold on a little bit tighter to those last two that are left. When the next one comes off, it's going to hold on even tighter to that last one. So you can think about it in that terms. Loss of the second or third proton occurs less readily than the first. That's what we just said. Okay. This one. For a typical polyprotic acid in water, only the first dissociation step is going to contribute significantly towards the hydrogen ion concentration. When we say that they're greater, we mean they're a lot greater. So if I'm looking at something like phosphoric acid, you may be given 3 different Kas. You only care about the first one because all the other ones are going to dissociate, but they're going to dissociate at such a small amount, they're not really contributing to the hydrogen ion concentration. We're not going to calculate this because we can do that. Okay. We don't actually write any of them. They're all so small. The dominant equilibrium is a dissociation of the first one. Okay, so you could plug that in there. You all know how to solve this math. You know how to do it already. We're just going to blaze through it real quick. Okay, you could do your little ICE table there. Figure this out. Put your equilibrium in there. Okay. Figure out your pH of 0.72. Okay. And you could go through the whole step pulling off a proton at a time. Okay? So that's your, notice how the Ka has moved significantly from the -3 to now -8. Okay? Okay, we could do that. Sulfuric acid. Sulfuric acid is a little different, right? It's polyprotic. It's got 2 protons. The first one comes off and acts like a strong acid. If you remember, sulfuric acid is one of our strong acids. So that first one that comes off is considered a strong acid. The second one that comes off is a weak acid. But look, that's still kind of on the larger side of the small numbers, right? This is very large. We know that first one. I dump it in there. That first one flies right off, no problem. Even this is considered a weak acid with a Ka of 1.2 times 10 to the -2. Okay, so in this case, the first piece that came off would be 100%. That means I would have 1 times 10 to the -2 molar hydrogen ions, but I would also have 1 times 10 to the -2 molar of HSO4 minus. And then I could use that Ka to calculate the rest of them. Okay? Because this is a strong acid, these 2 guys are major components. And then I would need to figure that out. All right. We could plug all this in, plug that in. Okay. We notice this is a ridiculous result. So we can't we can't make our usual assumptions in this case, and we would have to use quadratic, which is one of the reasons we can skip this, right? All right, there we go. That's our X and pH 1.4. There we go. All right. This is where I want to really start strong today is the acid-base properties of salts. So you remember solubility rules? We talked about things like being strong and weak. And as you go through looking at salts, as salts dissociate in water, they also have properties of acids and bases because of how they might react with those hydrogen ions or those hydroxide ions. So salt is just a name for an ionic compound that disintegrates into ions when dissolved in water. These have independent movement, and this is the key. In the context of this unit, they can behave as acids or bases under certain conditions. So that's really important. When dissolved in the water, salts that consist of cations of strong bases and anions of strong acids have no effect. Remember, what does strong mean? Completely dissociates. Strong falls apart. Completely dissociates. All right. So, if I have something like sodium chloride, right? Think about this whenever you're doing this. This is actually a simple way. This is the way I look at salts. So, let's look at sodium chloride here. I take NaCl, and I'm going to break it apart. My cation is what? Na, right? So this is plus, this is my cation, and my anion is Cl, and so that's going to be minus, right? Minus 1. I'm going to put plus 1 here. All right. I want to make an acid with the anion and a base with the cation. What that means is I'm going to turn this into NaOH and HCl. Why? So I actually want to do it because I want to think about, but that's a good point. In this case, the water's actually going to surround it. But I want you to pretend that this is sodium hydroxide. Pretend it forms that. What do I know about sodium hydroxide? It's a strong base. It's a strong base. That means this is not going to do anything to the hydroxide. What do I know about hydrochloric acid? Strong acid. It's not going to have any effect on the hydrogen ions. Y'all following me so far? What this means is if I have a salt that's composed of something that would be weak, right? So a weak acid might be, how about acetic acid? Okay. So what's the formula for acetate? Would y'all be okay with that? What happens if I put sodium acetate in water? Let's pretend that I made NaOH, and I'm going to write this in a funny way. Okay. And that's acetic acid. What effect does the sodium have on the hydroxide? None. What effect does the acetate have on the hydrogen ion? It does what? They're going to stick together. So what happens to the free hydrogen ion concentration? The free hydrogen ion concentration goes down. If the free hydrogen concentration goes down, what happens? So if I decrease the hydrogen ion concentrations, what happens to pH? Increases. this in a nutshell is what we're talking about. This comes back to the common ion effect. This is what I'm saying. So my suggestion to you is take these and rewrite them in terms of a hydroxide and a hydrogen ion. And then ask yourself, is this strong or is this weak? If it's weak, it's going to lower the concentration of whatever it's bound to. And if it's strong, it's going to have no effect. Everybody good with that? All right, now that you've gotten a quick overview, we'll dive in and see what we can do. If I find my remote, there it is. All right. So these are examples. These are all strong electrolytes or strong salts. They're going to completely fall apart, highly soluble. A basic solution is formed if the anion of the salt is the conjugate base of a weak acid. I can look at the Kb relationship for the anion from the relationship. Oh, hey, look, sodium acetate. So now that you've done that, let's calculate the pH of a 0.3 molar sodium fluoride solution. So real quickly, I want you to think about this. Like, let's do the concept first. So I've got sodium fluoride. So what two things do I want you to make? So I need the base. So the base would be what? And the acid would be HF. All right. What do I know about that? No effect, right? Because that's a strong base. What about this? It's a weak acid. So what effect is it going to have? We're going to do what to the hydrogen concentration? We're going to lower that. Okay? So let's just keep that in mind as we do this problem. Y'all good? So here's the Ka. Hydrofluoric acid is a weak acid. The major species will be sodium, the fluoride ion, and water when we start. Okay. This is a weak acid, so we're going to say that it has a significant affinity for protons, and then that's the dominant reaction. This yields the following Kb expression. Why is H2O not on the bottom? Because it's a liquid. Some of y'all keep remembering this from the test, so that's good. Good? All right. We can calculate the value of Kb from Kw and the Ka of F, of HF, right? Because we know Kw, it's a, what do we say? Yeah, it's a constant. It doesn't change. There you go. And I just gave you the Ka for the acid. So let's figure out the Kb. What else could I have done here, maybe? You could have taken the pKa and the pKw. And the pKw is going to be 14, right? So the pKa, and oftentimes we start using that to make our lives easier. And so I look at the pKa, and then I can find the pKw, or the pKb. Sorry about that. All right, this is our Rice table here. Here's our reaction, our initial change in equilibrium, Everybody good? Pretty standard stuff we've been doing, for months now. We're going to say this is basically 0 to start because we don't care about it. We're going to add a bunch because that's going to be corresponding to how much we make of this as well. Okay? So our x is 2.0 times 10 to the minus 6th. You guys should do the punchy and make sure that makes sense to you. You should have your calculators. Is this what your calculator said? All right. So if that's 2.0 times 10 to the minus 6th, that is the same in this case when I'm doing any multiplying. So my POH is 5.69, so my pH must be right. There you go. Cool? Y'all see how that works?
Yeah.
Pretty straightforward. The solution is basic. And that's what we would expect, right? Okay. Let's look at the dissociation of hydrocyanic acid in water. All right. I'm looking at this. I've got a Ka of 6.2 times 10 to the minus 10th. Okay, cyanide is going to look to be a strong base in this particular reaction. Hydrocyanic acid is a
Weak acid. Strong acid.
That's a good question.
Okay.
What are your strongs?
HCl.
Not that one. That's how you know. Yeah, there you go. That's how you know. So I've got a Ka of 6.2 times 10 to the minus 10th. All right. This is going to be, remember cyanide's one of our minus 1s. They fall off really easily. Okay. So this is what's going on in this reaction here. And I've got my Kb is Kw over Ka. That's all I'm going to do is I'm going to flip these. You guys can do this all day long. I'm usually going to give you a Ka. You're going to have to calculate Kb or vice versa. The key here, this is like different than what you've been doing. It's the same thing as subtracting the 14 from the P's. All right, so the pKa, pKw. All right. Right. This is going to compete with the hydroxide ions for the H+. You following me? The Cn is going to pull the hydrogen ions away, therefore lowering so my order of base strength is going to be the hydroxide, the cyanide, and then the water. Y'all good? All right. Some salts that can produce acidic solutions. So when the anion is not a base and the cation is the conjugate acid of a weak base. So ammonium chloride, right? Salts that contain highly charged metal ions. Aluminum chloride. The higher the charge on the metal ion, the stronger the acidity of the hydrated ion. What do we mean? Well, let's look at the pH of a 0.1 molar ammonium chloride solution. Y'all good? The Kb value for ammonia is 1.8 times 10 to the minus fifth. Remember what we talked to you about ammonia. Ammonia acts as a base. Is it a strong base? No. No. Because remember, you know your strong bases, right? Your 8 strong bases. Lithium down, up to calcium, right? 5 down, 3 up. Yeah, so that's not in that list. So I know it's a weak base, and in fact, the Kb value for this is 1.8 times 10 to the minus fifth. So what's going to happen here is, if I mix that into water, it's going to take in that extra hydrogen. That's in fact how we get the base. So the major species are ammonia, chloride, and water. Both the ammonium ion and water could produce the hydrogen ion. The dissociation reaction is this. The ammonium ion dissociates into ammonia and hydrogen ion. Oh, yeah, there's your Ka. Good? Important thing to note. All right, the given value for Kb is used to calculate Ka for NH4+. And we use the same relationship. This is the same math. So you know what it's checking out. There we go. So the Ka for the ammonium ion is Kw, and the Kb for the NH3. Just be aware of what it is you're actually calculating for. Although the ammonium ion is a very weak acid, it is stronger than water and will dominate in the production of hydrogen ions. Notice that number there, right? Yes, it's a weak acid, but it's stronger than water. Okay, so we're going to focus on the dissociation of the ammonium ion to figure out what the pH is in this case. It's in your notes, right?
Yeah.
Okay,
Page 20.
good.
Wait, so is that's Ka, 5.6 times 10 to the negative 10, right?
Yes, yes, that's the Ka for the ammonium ion. All right, set up our little rice table. And hopefully we plug that in. Y'all okay? We did our little approximation again. We got rid of that x squared. You're able to multiply this, put it in your calculator. You know how to actually do this in your calculator. And so you got it right. Did you test it? Did you actually punch it in? Did you actually move your fingers over the buttons?
Yes.
Okay, good. So you got 7.5 times 10 to the minus sixth. The drawer that says calculators.
Appropriate name.
Plywood.
Good? All right. Yeah. All right, so there we go. So we end up with a hydrogen ion of 7.5 times 10 to the minus 6. Therefore, the pH is 5.13. All right. Here's some quickie rules that will help you in your life. If the Ka is greater than the Kb, okay, this is for solutions of salts when both the cation and the ion have acidic or basic properties. Okay, if the Ka is greater than the Kb, then the pH is less than 7. This is its tables in your book. If the Kb is greater than Ka, the pH is greater than 7. It's basic. And if they're equal to each other, as you might imagine, that's going to be neutral. I know we start out this unit talking about dissociation being temperature dependent. I am still going to tell you, for testing purposes, we're going to be talking about stuff at 25 degrees or 298 Kelvin. So all these sort of normal rules apply. They may ask you a thought question about raising the temperature, how that affects pH, but that's not going to change. It's not going to change for actual problems with pH.
Just a reminder.
Yep.
So the pH going down doesn't necessarily mean that that the solution itself is more acidic if the temperature changes, right?
If the temperature changes, but again, typically, all our math, all our calculations, and they'll tell you right at the start of the test that assume everything's at 25 degrees, which is 298, unless specifically stated otherwise.
Okay.
But yeah, if I can actually make the pH go down, if I increase the temperature, the pH can drop and it still be neutral because I've got more hydrogen ions, but I also have more hydroxide ions. Yeah. Okay. All right. Let's see. Let's predict whether an aqueous solution of each of the following salts will be acidic, basic, or neutral. Ammonium acetate and ammonium cyanide. Let's think about that. Just make some guesses here. Acidic, basic, or neutral? You all ready? Got some mental guesses here? I've got ammonia and acetate. What do I know about both of these? They're both weak, right? What do I know about them now? The Ka is 5.6 times 10 to the minus 10th, and the Kb is 5.6 times 10 to the minus 10th. What do we think is going to happen? It's going to be neutral. They're both weak, but they're both equally weak, so, you know.
Oh. They're both weak.
Good? All right. How about this one? I've got ammonium and chloride. Not chloride, cyanide. The value for ammonium is 5.6 times 10 to the minus 10th, and apparently that's really annoying. The Kb for cyanide is 1.6 times 10 to the minus 5th. Okay. The Kb for CN is much larger than the Ka for ammonium. Okay. That's going to be a stronger base, so the solution is going to be acidic. Going to be basic. Good? Makes sense, guys? Just compare the numbers to each other. Make sure they will often give you the Ka values. Do they do that here? I don't know if they did that for cyanide. Nope. Did it earlier. So they will give you, like if they gave you this Ka values for cyanide, before you can make that comparison, you've got to convert that to Kb. Okay? All right. If solid sodium cyanide is dissolved in pure water, is the solution acidic, basic, or neutral? This is the kind of question that you'll see, and the quick and dirty is to make acids and bases out of them. What do I know about sodium? Strong. So it's not going to have any effect on what? The hydroxide. What do I know about cyanide? It's weak. So it's going to have it's going to stick to the what?
To the hydrogen.
So it's going to do what to hydrogen? So
Increases the pH, which makes it
basic. You guys good? Yep, that's going to be basic. Yep. If solid ammonium fluoride is dissolved in pure water, will the resulting solution be acidic, basic, or neutral? For ammonia, the Kb is 1.8 times 10 to the minus fifth, and for HF, the Ka is 7.2 times 10 to the minus fourth. So do some quick math. Y'all good?
Yeah.
Is that what you got too?
Yeah,
What'd you get?
I got acidic. Boom.
Good?
Did I have this during the test?
No. All right. Factors that determine whether a molecule containing an XH bond behaves like a Bronsted-Lowry acid. We're going to look at bond strength and polarity. We'll look quickly at hydrogen halides, oxy acids, and hydrated metal ions. Okay. Remember these. The reason hydrofluoric acid, because if you will remember, some of our strong acids include hydrochloric, hydrobromic, and hydroiodic, right? And many people ask, well, why isn't hydrofluoric a strong acid? And that's where we get into bond strength and bond length. This is a much stronger bond than this. Even though they're only +1 charges, remember fluorine's this little baby, and proton, of course, is really, really small, and they get closer together because of whose law? Coulomb's law, Coulombic attraction, right? Fluorine's little baby, hydrogen's little baby, they get really close together. And even though they're only +1, they're still close enough together, holding tight enough together that water's not going to break them up. Because water's really big in comparison. So these two guys can get really close together. They can have a high bond strength. It's going to be a weak acid.
You would think more strength would make them strong acids, but I guess but strong acids completely
Remember, strong falls apart.
Why are these weak acids the ones that dissociate?
Because strong
That would make
acids
more
get
sense.
all of them hydrogen off.
But still,
Because
that would
strong
make
acid, if you put it in water, boom, it's strong. All the hydrogens are now available. They're now acidic. They're now protons.
dissociate.
Yeah. Just remember, strong people fall apart, right?
I was thinking the weak have friends.
I like that one too. The weak ones have friends, yeah. All right. All right. You guys know oxyacids. These have the hydrogen attached to an oxygen and something else. Okay. Acid strength increases with the increase in the number of oxygen atoms. The reason is that we are adding more and more electronegativity. Okay? The oxygen atoms become more effective at drawing electrons away from whatever the rest of this is. Okay? This continues to polarize the OH bond. So basically the electrons keep getting pulled over. Okay? So this has what's this called?
Hydrochloric acid.
It's a strong base. Wait, I lied. Strong acid.
What's the name of it?
Oh. Okay. Hydrochloric acid.
What is it?
Perchloric.
Perchloric.
Right.
Hydro means there's no oxygens. Hydrochloric acid, that's just my little HCl.
hydro plus an L.
Yeah, exactly. This is perchloric acid. This is chloric acid. This is chlorous acid. This is hypochlorous acid. Good. All right. Follow me? All right. So perchloric. Look at that Ka.
That is huge.
Like a 10 to the 7th.
That's big.
Don't drink it.
Yeah, well, I wouldn't recommend drinking any of these. But what goes on here is these extra oxygens are pulling these electrons away. This is becoming very polarized, and that hydrogen ion can just pop off. Okay? This one too, and as I continue to lose oxygens, it becomes has a smaller and smaller Ka value. Cool? All right. Then I have sulfuric, and this is for the first one. Sulfurous. What's this called? Nitric acid. This is nitrous acid. Very, very large Ka, large Ka. Okay. Notice how nitrous is a weak acid. Nitric is a strong acid. Sulfuric. Yeah. So the sulfuric acid, strong, sulfurous acid, weak, although not really that weak, but okay. Okay. Here's some Kas, some more electronegativity values of the X, and how that affects the Kas. All right. Hydrated metal ions kind of look like this, do the same thing as the oxyacids. So we can take a look at that. All right. What kind of factors below look at whether or not it's going to behave as a Bronsted-Lowry acid? Who determines whether or not this is going to be a Bronsted-Lowry acid? We just talked about it.
One. Wasn't it both? You said we were going to talk about strength and polarity.
What's that? Well, it really has to do with the strength. I mean, the length and the strength are related to each other, right? The shorter, the shorter the stronger, yeah. So, it's probably not a great question there. All right. Let's see. Acid strengths and oxides. Compound containing this group produces acidic solution if this is strong and covalent, and it's basic if that is ionic. This should make sense, right? If that's ionic, what do I have left? If this is an ionic bond, that's going to form, yeah. Okay, let's see. Low electronegativity leads to ionic and weak OX bonds. Okay. Let's see. Do I need this? I don't think so. Okay, yeah. See, ionic oxides dissolve in water to form basic solutions because the oxide ion has a high affinity for protons. So calcium oxide, if it dissolves in water, the calcium's just going to do its thing, but the oxygen, the oxide, is going to snag up those hydrogen ions, right, become hydroxide and leave hydroxide. Okay, so those are going to produce hydroxide ions. Is that making sense?
Yeah.
If these two guys split up, or if this guy splits up and I drop that in water, I'm going to have hydroxide ions because the oxide by itself isn't happy. It's going to snag one of those available hydrogen ions. And now I have hydroxide that's left over because I've lowered the concentration, the available concentration of hydrogen ions. Yeah?
If you were to put that in water, wouldn't it form two hydroxides? Because the water would, one of the hydrogens would go to the oxygen that's binding to the potassium.
Exactly.
All right.
Exactly. Yeah. So it's not just a case of lowering the hydrogen ions. I'm lowering the hydrogen ions and also creating additional hydroxides. All right. Yeah, we don't need no Lewis stuff. Who cares? Lewis can run away. We're all done with chapter 14. So now
No.
we're ready for 17.
7. What about 15?
I mean 15.
What was I saying?
I think we should call it a day.
No.
I have like 30-ish minutes. Oh, that's a personal problem.
Are you okay?
He's fine.
What?
What's the next one? He tripped on a
I
curb.
don't know.
Huh?
We have
next
I didn't bring my
one?
stuff today.
My brother tripped on a curb.
No, I can't stop.
Which one is the next chapter?
Do you want me to go and pick
Do we
you
have
up?
the notes for the next
Really? 'Cause he
Yes.
tripped on a curb? Oh my. Oh my god.
Where?
He's literally fine.
I don't already have these. I have an extra copy.
With us.
Oh, but
Yeah,
we
it
did
fell.
these.
Apparently.
Someone take it.
I
No, I
know.
have one too.
So he's over there like, you're mad. Look, he's like, yeah, I'm good. I tripped on a curb.
Is the curb okay?
Yes, he's fine.
Is the curb okay?
Oh, probably not.
All right.
Acid-base equilibria.
All right. Acid-base equilibria.
Oh,
You know, no. Do we have? No.
Yes. Yeah, they literally say acid-base equilibria.
oh.
Oh, right there.
Do I have that? I don't remember.
Not forgotten by the last one.
Sorry, it's
Too fast
TikTok.
for me to read.
Speaking of a TikTok, I tagged Melissa in it and I try to send it to you, but Remind doesn't let me send videos. So I'm just going to show it to you because this is how I feel. Because of you.
Well, if you do your homework, it'd be okay.
Yeah.
Well, you sent me the one about, did you do the back of the quiz?
Yeah. What back? Oh, is it over there? McKenna, since you're up.
And like ice.
That is how I feel.
All right, cool beans. Let's do acid-base equilibria.
I thought we already did this.
So this is, yeah, this is different. This is the buffering. So yeah, so I think it's the buffering one. All right. So this is going to be solutions of acids or bases containing a common ion. We've been doing common ion. You know how to handle this. We're going to talk about buffered solutions and buffering capacity. Then we're going to talk about titrations and pH curves. Unfortunately, we won't get to do one. We may do one after your exam, after your chill, and relax. There's nothing else to do. So we'll spend some time after that. We'll do probably a titration will be one of those available, and those are lots of fun. We'll talk a little about acid-base indicators. Again, for those of you who were with me 2 years ago, you got it. And then those of you last year, I did a short little video on it that I think a total of 30 people out of all the classes watched.
If it was on, yeah.
Are those the pH papers?
Yeah, it's pH, papers, and lemon juice, and Gatorade. And,
Part of a chapter just dedicated to that?
yeah, exactly. We're not going to talk about polyprotic acid titrations, but they exist. All right, common ion effect. This is stuff we've been through. You know how to handle this. The shift in equilibrium position, which occurs due to the addition of an ion that's already involved. Because if I increase a common ion, if I were to do something here and I increased chloride, what would happen?
More acidic.
If I increase chloride here, what would happen to this reaction?
Oh, it should left.
It would go back to left, right? That's the kind of stuff I want you thinking about. And I know the Chalier's principle only applies once you're at equilibrium, but you can think about it, what's going to happen to the system, right? All right, so let's look at, I have a solution of ammonium chloride, and I have a 1 molar ammonia solution. If I add ammonium chloride to it, okay, The production of the extra ammonium ions will cause a shift in the position of the ammonia-water equilibrium. So this is my current equilibrium. If I add this, if I increase this, what happens to this reaction? If this gets increased, it shifts where? It shifts back left. If it shifts left, it's going to do what to that? Decrease it. If I decrease the hydroxide ion concentration, what happens to the pH? Decreases the pH. Y'all follow me? This is the thought processes. I really want you thinking. Yes, we can all calculate, but I want you got to chew on this a little bit. In solutions containing polyproducts, just worry about the first dissociation. The equilibrium concentration of hydrogen ion in a 1 molar hydrofluoric acid solution is 2.7 times 10 to the minus 2. All right, percent dissociation is 2.7%. Let's calculate this. If I have a solution that has 1.0 molar hydrofluoric acid and 1 molar sodium fluoride. What do I know about sodium fluoride? It's a strong
Strong. Base.
salt. It's a strong salt, right? It's going to fall apart completely because of the sodium, right? Sodium's one of my alkali metals. This again is, and because we're doing solubility with the babies right now, and I'm really hitting them hard to get those solubility rules memorized, right? You need to know that this is a strong salt. It falls apart completely. So we have strong acids, strong bases, and strong salts. This falls apart completely. That means I don't need dissociation constants, right? Because if I've got 1 molar sodium fluoride, I have how many moles of fluoride ions now? I have 1 mole of it now. I have exactly the same as this. As a caveat, all of y'all recognize that nothing totally falls apart. But we're going to pretend it does because it makes our life easy.
Well, nothing's ever exact.
Exactly. It's chemistry. All right. So here's our gray math. Here's our species. I've got my hydrofluoric acid. This is a weak acid, so it's going to primarily be together. I've got the fluoride ion from here and the sodium ion from here that I really don't care about, and water. Everybody follow me on this? This completely falls apart, so these become major players. All right, here's my equilibrium equation, the one I actually care about. This is my hydrofluoric acid falling apart. The equilibrium expression can y'all use the common ion effect you've already done and solve this? Please go ahead and do that. What would go here? We don't know. That's an X. What would go here?
One.
I don't know that one. I know the one below it is
Point
going to be 1.
5.5. 1x. 1x.
X.
X1. 1x plus x.
Right.
Oh.
So this is X.
Oh, yeah.
This has got the 1 molar solution, right? So I've got 1 mole of fluoride ions plus whatever that X happens to be, right? And on the bottom I've got, what is it, that one? That one minus whatever the X happens to be.
What in the world?
Okay.
There's our little table there. You got your little table?
That is so rude.
That's rude.
Y'all following what we're doing here? So now I just take this set it back up into your formula. Now we're going to say that X is going to be really, really small. That means I can ignore it not just in one place, but in two places in this equation. So what is X? Can you do it without a calculator?
7.2 times 10 to the negative 4.
Yay! We're all calculator free. It'd be kind of good if, like, every time you used a calculator, you got an electric shock.
I would do it. You sure that would be good?
Yeah. So you could still use it. There'd just be a price to pay every time you decided to use it.
Like a calculator, like a calculator on your phone.
The hydrogen
Yes.
concentration was equal to the Ka.
Yeah, in this case, just because of the way that, because they were nice enough and gave us nice simple numbers. But you know where'd this one come from? Where'd this one come from?
From the one plus X? From
Sodium fluoride.
The sodium fluoride.
Okay.
And this one came from the hydrofluoric acid. The one downside of using cute numbers like this where they make our math easy is people can forget where they come from. So it's nice to remember that that one came from the sodium fluoride and that one from the hydrofluoric acid. All right. So salts, we know how the salts affect. Good? All right. Let's keep going. And so your pH of 3.14. The percent dissociation, 0.072. What's that? pH of 5.
No, pi.
Pi. Oh, pH of pi. I got you. pH equals pi.
Oh.
Yeah.
I'm still falling. What can I?
Oh, wait. Sorry.
It's all good. It took.
I was looking at the I used to like 300.
Wow.
I know,
Yeah, we had a
but
competition in 6th grade and I messed up around 90 something.
Wow. I think 30 is as far as I ever got.
I know 10 off the top of my head and no more.
Yeah, I was
Yeah, and then, yeah,
9, 6, 5, 3. That's all I have.
I get to the 9, I stop.
I get to the 4. We stopped it.
I
They
stopped
forced
at
us
the
to
3.
learn it in 5th grade. Or if you want to double stupid periodic table.
All right. Let's look at these values right quick here. The values for hydrogen and the percent dissociation with a 1 molar solution, okay? The presence of the fluoride ions from the dissolved sodium fluoride greatly inhibits the dissociation of the hydrogen or the hydrogen from the hydrogen fluoride. I shift this back to the left by the presence of the fluoride ions. Y'all follow me? I put a salt in there, in this case sodium fluoride, and I shifted the whole thing back.
Right.
Okay. Which of the following statements is true? The hydrofluoric acid dissociates more readily in a solution of sodium fluoride than in pure water. Dissociates equally well in a solution of potassium chloride and in water. And does not dissociate to any extent. What you got? Is A true?
No.
No, we literally just disproved that, right?
Yeah.
What's the deal? What effect would having potassium chloride have on hydrogen fluoride?
Well, potassium.
Is there any common ions?
No.
Nope. And in fact, potassium hydroxide would do what? Is that a strong acid or base?
No.
It's a strong base, so it falls apart completely, which means the potassium is going to have no effect on the hydroxide. What about hydrochloric acid? Strong acid, so it's going to have no effect on the hydrogens. So if I have no effect on the hydrogen ions, I have no effect on the hydroxide ions, and I'm not a common ion to the acid, I'm going to have no effect at all. So having hydrofluoric acid is going to dissolve just the same in a solution that has potassium chloride as it would in water. Get it? There's nothing in common, and I'm not affecting the, there's no common ions, and I'm not affecting the hydrogen ions or the hydroxide ions. If I'm not affecting any of those, there's no effect. Okay. Let's see what the next one is. All right, there we go. Buffered solutions. All right. So, buffered solutions. You got a question? Is there a question? Okay. Let's talk about buffered solutions. They resist changes in pH when either the hydroxide ions or protons are added. So your blood is buffered. A lot of times when you take medicine, the medicine has to be buffered. You can take buffered aspirin. A lot of people recommend that for people who are taking daily aspirin for like heart preventative stuff. They recommend a buffered aspirin if it's upsetting your stomach. Okay. Your blood has to stay at a certain pH. What is that? Some of y'all who earn, what's the pH of blood supposed to stay at?
3.5. I'm just kidding.
It's like 7.2 or so.
It's a 7 something.
It's a little bit. It's a little bit. 7.2.
That's a good question. Okay.
Ask Siri. My God.
I think it's like, I thought it was like 7.2, 7.4, somewhere in there.
7.35 to 7.4.
Yeah, 7.4. There you go. All right. So interesting. That's slightly basic, right? Cool. But your blood is buffered, so you don't have these wild swings in pH. That would be bad. And when I mean wild swings, I mean the 0.01 wild swings. You really want to keep it tight, and the reason for that is the proteins they fold appropriately or not based on pH. And so if you've got a disease that messes with the pH of your blood, it can wreak havoc across your whole body. Okay, it's not a good thing. All right, so a buffered solution contains a weak acid and its salt. And buffering is possible at any pH. So I can do that, but I need to appropriately pick the components I'm going to use based on the pH range that I want to buffer. So you can use up a buffer, you can blow a buffer away by overloading it. But buffers can actually take up a lot of slack, as it were, in terms of protons or hydroxide ions. So a buffered solution could contain 0.5 molar acetic acid and 0.5 molar sodium acetate. What's going on here? So if I'm wanting to adjust, let's say I've got this here and I add some hydrogen ions. So acetic acid's already a what kind of acid? Weak acid. So it's going to hold on to hydrogen ions, right?
Right.
It's going to have some dissociation. It's looks like 10 to the minus fifth there. What happens if that hydrogen ion falls off? Pretty quickly, what happens? It goes back on, right? Before it can do any damage, it's going to get stuck back on. What happens if I have excess acetate and I add some more hydrogen ions? Those hydrogen ions do what? They stick to these extra acetates that are here. Right? Now what happens if I add hydroxide ions?
The sodium will break off and go with the...
Not the sodium. Sodium's strong. It's just going to pull off one of these guys. because they're falling apart and coming off. So it's going to grab, the hydroxide is going to grab one of these guys. So these two things are working in conjunction with each other, a weak acid and a salt of the weak acid. All right? Now, you got to be careful. You're going to want to use one of your alkali metals, right, as your cation. So it completely falls apart, and you're basically left with these guys. So how does that work? Well, let's calculate the pH of this solution. Here's my major species. This is not going to have any effect, right? Because sodium forms with hydroxide, it's strong. This does not affect hydrogen ion concentrations or hydroxide. This is a base. It is the conjugate base of the acetic acid. So these are my major components. And I've got water, of course. Everybody following so far? Those are the things that I've got my major species in. The acetic acid dissociation equilibrium is what is going to control the pH of this solution. That's it right there. It doesn't really matter that I've got a bunch of excess. It doesn't matter that I've got a bunch of excess of acetate here, okay? Because even if I drive it back that direction, I still don't have that many free to take up. Okay. So here's my, you got your reaction here, right? Because that's aqueous and aqueous and aqueous. Here's my initial concentration and my equilibrium concentration. Go ahead and write that out. You got it all written down? Stop lying. All right, get this down. So go ahead and solve this equation. Again, notice we use some super high level math here. Again, where does this 0.5 come from? Acetic acid, and this 0.5 comes from, yeah, the acetate, from sodium acetate. Very good. So pH is 4.74. Y'all good with that? Hold on to that number. Make sure you've got it somewhere. Because I could change that. I could go back. Why doesn't this do this? I want to go back and do this one. All right. Here's what I'm going to do now. Back to the original problem. Now I want to add something else. And this may require a little bit more math. What if I have 0.01, okay? So I have 0.01 molar HCl. And this is what I really care about, right? Because the chloride's not going to matter to anything. Now I want you to do the same math. Do the same math. Except here, this is going to be x plus what? 0.01. Just want to see what happens. What'd you get? With the 0.01? What'd you get? No, x plus 0.01. So it's the same thing here, right? So 1.8 times 10 to the minus fifth. What's the pH? So y'all did all that. I've added 0.01 mole of hydrogen ions, and I end up with a pH of basically 4.74, right? That's what this thing does. That's what this buffering does. The buffering absorbs the fact that I just added. Now imagine if I'd added 0.01 moles. If I added 0.01 moles of HCl to water, water would move from a pH of 7 down to a pH of what? 2. Without a buffer, if I'd added that much just to pure water starts out at 7, it would go down to 2. But I had a buffer, and my pH basically stayed the same. This is what buffers do for us. I mean, that's a lot, right? Would y'all, I mean, pH 2, if I added that, okay. Oops, there we go. So now let's calculate the change in pH that occurs when a 0.01 mole of solid sodium hydroxide is added to 1 liter of the buffered solution that we just made. So you guys have those numbers, right?
What?
So I just told you, we just gave you an example about the acid. Now I want to do the same thing, except we're going to do it with a base. We're going to add 0.01 moles of sodium hydroxide to 1 liter. Now why did we do that? Why did we use those numbers? To make our life easy, because 0.01 mole over 1 liter is 0.01 molar, right? And I want you to go ahead and calculate that and then compare this change to that which occurs when I add this to water. If I add that to water, that means I have 0.011 mole NaOH. If I add that to water, the water starts out at pH 7 and goes up to pH what? 12. Y'all good with that? Okay. Do the math and figure out what the pH would be by adding 1 mole of solid sodium hydroxide. Sodium hydroxide, that means hydroxide is going to be a major component. There's my reaction. The hydroxide ion is going to take one of the hydrogens off. You can think about it that way. Okay. It's going to convert that to water. Now it's a liquid. It's no longer part of the equilibrium. And I'm going to be left with acetate, which is fine. I've got plenty of acetate floating around anyway. A couple of things. We're going to assume the reaction goes to completion. Then we're going to carry out the equilibrium calculations. There's our stoichiometry. I'm going to convert. It's going to just assume all of it gets used up. And so basically the 0.01 mole of acetic acid is now 0.01 mole of acetate. So I've added the 0.01 mole that was subtracted here. So the hydroxides get all used up. Now I have 0.051 moles. And the beautiful thing is now we can just do our math again. And it's a beautiful thing.
I want to go home.
Okay.
We should stop.
So after we complete this, I no longer have any hydroxide. And the dominant equilibrium is simply the dissociation of the acetic acid. There's our Rice table. Notice the difference. The only difference, we added this much, 0.01 moles of sodium hydroxide, and this is what was changed. I start out with a little bit less acetic acid, and I end up with a little bit more acetate. How do you think that affects our math? A lot or a little? Just a little bit. Because, yeah, it's still pretty close. Okay. There's our normal procedure here. So I go from 1.8 times 10 to the minus fifth to 1.7 times 10 to the minus fifth. So our pH is almost the same. In fact, it's what? 4.76?
4.77, he rounded.
Did he round wrong? Oh, well, it's because he used this rounded number instead of using the calculated one, right? So we went from, what, 4.74 to 4.76, even though we added a whole 0.1 moles of sodium hydroxide. That's a lot of sodium hydroxide, and this little solution basically took that up without changing the pH.
We have a 48 question quest due this Thursday.
What?
Is it?
Yeah. Yeah.
Okay.
I read it.
So pH is increased by 0.02 pH units. We went from a 5 pH units is how much we would have moved without this buffer. So buffer's really important. You need to know.
Wait, so where did we get 0.5 from? Just given at
Where?
I didn't see it.
Which 0.5?
There was a 0.5.
Oh yeah, I was given in the original problem.
Oh yeah, all right.
He opened it.
All the way back there.
Yeah.